Hi, I'm Simon Safetis, and I'm presenting our joint work titled Sample Efficient Learning of Novel Visual Concepts, in which we propose a few-shot learning approach that utilizes a neurosymbolic architecture to detect novel objects as well as non-visual attributes and affordances in an efficient manner. As a motivating example, let's take a look at the image to the right. A neural object detector may detect a person and a motorcycle. However, we would also like to know that a motorcycle is driving on the road. While this deduction comes naturally to a human, neural networks struggle with this conclusion that motorcycles require a road that affords it to drive on. Thus, we propose an approach that is able to infer more abstract concepts like attributes and affordances by utilizing symbolic knowledge in the form of a knowledge graph, which also allows the users to easily add new concepts in a sample-efficient manner by extending the knowledge graph with new nodes directly. In particular, we aim to combine the benefits of neural networks, namely their ability to process high-dimensional inputs like images, with knowledge graphs that allow for easy interpretation and extension. Our work improves our prior approaches by conditioning the graph search on a global image context and proposes an automated way to incorporate novel information into the graph. On a high level, we employ a three-staged approach that utilizes neural networks to pre- and post-process the inputs and outputs of the knowledge graph. First, we utilize a pre-trained vision pipeline that detects a small set of objects used to initialize the knowledge graph and generates a global image context. Then, we employ a graph search approach that propagates the initial objects through the graph in order to search for relevant related information. Finally, we employ a neural classification head to the graph output in order to create our final predictions. In summary, our contributions include a novel approach for few-shot object recognition that is also capable of learning and inferring abstract concepts, including attributes and affordances. Let's look at each of these three components in further detail. First, we employ a pre-trained faster RCNN to extract a set of initial object candidates, as well as a global image embedding utilizing VIT. The detected objects and the global image embedding are then used in our three-staged modified graph search approach. First, the detected objects, shown here in red, are used as a starting point in the knowledge graph. We then use these initial concepts in the propagation network to find additional candidate concepts that are directly connected to them. In order to do this, we calculate the latent representations conditioned on the neighborhood and the global image embedding for each of these blue candidate nodes. However, as multiple rounds of propagation would cause exponential growth, especially if the graph is large, we utilize an image-conditioned importance network that dynamically prunes the graph after each propagation step, leaving only 2 of the initial 4 candidate nodes. The 2 remaining candidate concepts are then locked in, and the propagation continues for t steps, dynamically extending the subgraph of relevant concepts. In a final step, we generate embeddings for all relevant nodes before passing the information to the classifier. Here's the overview of our inference pipeline again, showing the final classifier as a single fully connected layer, considering the relevant concepts, overall image embedding, and the initial object detections. Here are a few examples of our graph propagation. We start off with the red nodes from the neural object detector and then propagate the information through 3 rounds through the graph. Given the information in the graph, which serves as background knowledge, the system is able to find non-visual attributes also, for example, that the cars are parked and that the truck is large. An interesting observation here is the person node. It was mistakenly found by the object detector and assumed to be relevant. However, the image condition propagation and importance network never expanded further on this node, demonstrating the ability of our method to focus on relevant information. In our experiments, we utilized the VGML dataset, which is a subset of visual genome, providing a knowledge graph for the 200 most common objects and 100 most common attributes. We then extend the 200 object classes with 16 more classes to cover the entirety of the CoCo dataset. This then allows us to utilize a common novel object detection benchmark over the CoCo dataset, resulting in a training dataset with over 300 concepts and over 100,000 images total. After training, novel concepts can then be added by a human user by specifying the desired concept, for example, stadium, and providing a diverse set of 5 images that show how that novel concept is being utilized. We then automatically add and connect the novel concept to the knowledge graph and add an additional output node to our classifier. We then, in an sample-efficient manner, fine-tune the propagation network, train the node bias for the new node, and train the new weights in the final classifier in order for the new concept to be predicted. To automatically connect the new concept to the knowledge graph, we propose Relate. Relate uses globe word embeddings for each existing concept and their respective image patches to create a context-dependent latent representation of all concepts active in the provided set of images. Then, Each latent representation is paired with a novel concept in order to predict whether or not an edge should exist. We then train and fine-tune the relevant parts of our approach, namely the node bias, propagation network, and final classifier, from a small augmented dataset containing the sample images. We interleave this dataset with another small dataset of additional samples that contains images that activate each node in a knowledge graph at least once in order to prevent catastrophic forgetting. Relate automatically creates a knowledge graph with 16 novel concepts, and we compare the performance of a handcrafted graph with the same concept to the one created with Relate. Our experiments show that Relate does not negatively impact the model's capability of being able to detect the original concepts. Further, the knowledge graph created by Relate provides a source of information that is at least as good as the handcrafted knowledge graph. Thus, we conclude that Relate is capable of incorporating novel information into the graph in a meaningful manner. We show the results of our method in detecting the 16 novel objects from the CoCo dataset and compare the results to 3 state-of-the-art baselines, as well as 2 interpolations in which we only extended the classifier but not the knowledge graph, and a version in which the classifier and graph are extended but the propagation network is not fine-tuned to properly utilize the novel node. In each experiment, we trained all 16 classes on 5 sample images each and reported the average MAP score for all models. As a reminder, during training of our model, we utilized a small additional dataset to prevent the model from forgetting prior classes. However, this additional dataset did not contain any information regarding any of the novel classes. Our method provides a state-of-the-art performance when recognizing novel objects, despite being trained on a different dataset as compared to the baseline models. Marginal performance improvements can also be found if training our model directly on the CoCo dataset. We also demonstrate results in learning novel, non-visual concepts like attributes and affordances. In particular, we conducted 2 different experiments with 5 and 15 images for each of the concepts shown in the graph on the right. For example, we showed the concept of edible with sample images in the context of pizza, sandwiches, and hot dogs. Given 5 and 15 images, we reach a success rate of 67 and 75% respectively across our 100 test images. Among the test images, half of them show the targeted concepts in one of the demonstrated contexts, while the other half does not. We have also compared our approach against some of the recent multimodal language models with the goal of evaluating whether the knowledge encoded in these models can aid in inferring compound concepts. In our case, a compound concept refers to the model's ability to infer a higher level concept of, for example, a kitchen, given the detection of a fridge, microwave, and stove, while a microwave alone might not necessarily mean that we are in a kitchen. For the comparison, we tasked each model with deciding which compound concept is present in a given image and reported the respective results. As most of these models produce free-from natural language descriptions, results have been manually evaluated with regard to the desired target concept. Despite our model being outperformed in some category, our approach maintains the highest overall performance. In summary, we propose a novel approach for few-shot multi-label classification over visual and abstract concepts capable of automatically integrating new information into its internal model. Our approach outperforms current state-of-the-art novel object detectors, and our code and pre-trained models are available. Please check out our paper and code containing further details and additional experiments. Thank you for listening.